Yeah.
Okay. Okay. So, uh, so let me introduce you to the students. Then you will start, sir. Uh, Good afternoon to everyone. I welcome all of you to the 32nd lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce you today's speaker, Professor Piju Gandhi Ghosh from Vishwabharati University, Shantiniketan, West Bengal. Professor Piju Gandhi Ghosh works in several areas of physics, including high energy physics, mathematical physics, quantum physics, and condensed matter physics. Professor Ghosh did his PhD at the Institute of Physics, Bhubaneswar, which is one of the premier institutes in physics in India. He carried out postdoctoral studies in and abroad and joined as a reader in Vishwabharati University, Shantiniketan in the year 2005 and elevated to professor position in 2011. He lived in Japan about a couple of years and visited few other countries under bilateral exchange program. He delivered lectures in several forums. When I wrote to him to deliver a lecture in this forum, he immediately accepted. Also, he encouraged me to upload all the talks in the web so that it will be useful to the entire nonlinear dynamics community in India. We have uploaded several talks and will complete the process soon. With this short introduction, now I hand over the session to Professor Ghosh. Over to you, sir.
Thank you very much, Professor Senthil Velan. Firstly, for organizing such a wonderful series of lectures, almost for the last few months, and also thanks for inviting me to give a lecture on my work in nonlinear dynamics. And I have been also told most of the audience should be MSc first MSc final year students. So if I spend some time on the very elementary things of the topic, then it will be students. So I have my best to present the basic ideas in a very elementary ways. But in any way, if the student have any question at any time, they can, with the permission of the chair, me and ask me questions. I'll be happy to clarify the points. Okay, and there are experts in the audience also. So if I am talking two elementary things, excuse me, because this is only aimed at the students. Today I'll be talking about pseudo-unitary transformations and solvable models of nonlinear equations with loss and gain. And this work is done in collaboration with my current PhD student, Pushpendu Roy and Supriya Ghosh. Some of the work I'll be summarizing at the introduction also has been done in collaboration with my earlier student, Devdeep Sinha. I don't know, somehow I the talk using this bullet option that it will each slide will come one by one. It's not working here, or I cannot see how to do it. So pardon me for that. Any suggestion, Professor, how to enable that? Professor Senthil Velan?
Yes, sir.
So I wanted
Yes.
the talk is prepared where I can line by line, but I don't see enough. I mean, I cannot do that here. Do you have a suggestion that what should I do?
No, you go by line by line.
There must be some presentation mode, right?
Yes. Yes, sir. Now I think, let me ask my students, sir. Let me ask my. Sir, I think you can go as it is, sir. We are able to see the slides, so you just go ahead.
Bottom?
Yes.
Okay.
If you are not able to see, we tell you, sir.
So first, the title of the talk contains two words which may be unfamiliar to the students: pseudo-hermeticity and balanced loss system. So what I will do is that first I will introduce in terms of matrices what is pseudo-Hermitian matrix and what do I mean by pseudo-unitary. But these elementary discussions can be extended to any operators also. Okay, say quantum mechanical operator, or for that matter any mathematical operator. But I restricting my discussions only using matrices. So pseudo-Hermitian matrix, then pseudo-unitary. Then next I will be introducing this introduction to balance, loss and gain, and I will give examples from different domains of physics, namely mechanical system, non-relativistic classical theory, and nonlinear Dirac equation with balance, loss and gain. And my main talk will be concentrated around this non-relativistic classical theory, or the so-called, I'll be using some models of nonlinear Schrodinger equation. So the main of pseudo-unitary transformation will be shown by using this Schrodinger equation, which falls under the non-relativistic classical field theory. But since balanced system is a very important topic nowadays from the viewpoint of geometric theories and its immense applications in primarily in, and then also condensed systems or any other contemporary topic. So I decided that I will talk what are the balance loss gain system in the context of mechanical systems or classical or nonlinear Dirac equation, and then I specialize my talk by using this nonlinear Schrodinger equation. But of course, I should sorry, the method I am going to describe is in some modified form is applicable to mechanical system also as a nonlinear Dirac equation. And as I said just now, I'll be talking this pseudo-unitary transformation by using a two-component nonlinear Schrodinger equation, that is true for any n-component vector nonlinear Schrodinger equation, and the detailed calculation of exact Solution solutions, their power functions, and all these things will be done using this two-component vector nonlinear Schrodinger equation. Now, just hold a minute. Okay. Then finally, I'll be talking about generalized, namely, say, PT symmetry inspired generalized nonlinear Schrodinger equations. There are different kinds of generalizations. And then also, where we introduce some confining complex potential. There are, for last 1 decade or so, there is a new integral non-local nonlinear Schrodinger equation. So how to generalize all these to balanced loss gain system, that will be discussed. And then finally, I'll conclude my findings. Okay. Now, as I said, that first, let me introduce what do I mean by, or the general definition of a pseudo-Hermitian matrix. And simple example of a 2 cross 2 matrix, say H is 0, epsilon 1, epsilon 0, and following the standard technique of complex conjugation followed by transpose, consider the H dagger, basically adjoint matrix, then we can see that is not Hermitian for real epsilon 1 2. Epsilon 1 2 is real parameters. Sorry. Then if there the H is Hermitian only if epsilon 1 is equal to epsilon 2. Now that does not mean that the eigenvalues of matrix are entirely. That does not mean that eigenvalues this matrix is necessarily complex. Now, if we keep the eigenvalues, it's a very trivial calculation. We find that eigenvalues are square root of plus minus root over epsilon 1, epsilon 2. As you can see, that if any one of them is negative, say epsilon 1 or epsilon 2, since it's residing inside the square root, eigenvalues will be complex conjugate. But if the product epsilon 1, epsilon 2 is positive, then are positive. Okay? But if we calculate eigenvectors, then we can see that here for U, as I have used a kind of normalization. With that normalization, we can see that they are not orthogonal to each other. Okay. Now, this is the eigenvector. Now we take this u plus u plus u minus u minus. I'm for brevity. I'm using this Bryan-Tate notation. I understand that the MX students are at least familiar with this Dirac-Brachet notation. If not, this is basically u plus u plus. This means whatever you do, psi dx integration minus infinity to plus infinity normalization. This is meaning of that. Okay, u plus this eigenvector u plus eigenvector u minus. So normalization I have chosen. Note that if orthogonality condition, there are two eigenvectors, u plus minus is not is equal to 0, but it is 0 in a limit when epsilon 1 is equal to epsilon 2, but that is the limit H being Hermitian. So for the Hermitian case, everything is used, but non-Hermitian case, namely epsilon 1 and epsilon 2 not equal, then orthogonality is lost. So whatever you learned in the quantity textbook, that Hermitian operator ensures that eigenvalues are real. Basically, the actual term should be self-adjoint operator, but I'm not going into that details. And states are orthogonal. Here, we have a non-Hermitian matrix. Its eigenvalues are real in certain region, but its states are not orthogonal. So as a result, if you if you consider this a two-level quantum mechanical system and wants to see time evolution, see that unitary will be violated. Okay. Now, what we do also in the context of quantum mechanics or the vectors, we know about some completeness relation. You see that this completeness relation for this u plus u is also not valid. You can simply calculate and see that this relation bottom of the screen is not satisfied. I'm going to introduce what do we mean by pseudo-hermiticity. Well, we define some 2 cross 2 matrix intertwining operator as root of epsilon 2 by epsilon 1 0 0 epsilon 1 epsilon 2 with the condition that epsilon 1 epsilon 2 product is greater than 0. None of to 0, then eta plus is not defined, and product is 0 ensures the eta plus is a positive definite quantity. That means it can 0 or negative values. One can check a simple calculation. The H I have written in my previous transparency that H dagger and H are related through this relation, that is H dagger is equal to eta plus H eta inverse. This is the general definition of pseudo-Hermitian matrix. If H and eta are promoted to some operator in some Hilbert space, some other vector space, then also this is the same relation. But here, just to give you the example, I present it in terms of 2 cross 2 matrices. Well, what happens? Then we define a modified inner product, the standard V. That means, say, in terms of standard wave picture of equation, we use that psi star psi dx. So that is equivalent to U. psi star phi dx uv. We introduced some the vector space here for the case of matrix, and if introduce some metric, then norm has to be defined in terms of that metric. So modified norm or the inner product is defined like this, say u plus v. So if you want to think of say psi star phi, then this is like psi star theta plus phi dx minus infinity to plus infinity. Okay, so this is the, and if you want to work in terms of say this 2 cross 2 matrix, then you take the dagger of that, so it's vector, then eta plus matrix I have defined there, v is the column vector, perform the multiplication. Okay, so that is the modified norm in the eta plus space for uv. So important message for the students is that when we define density, basically it is related to some kind of metric in that vector space. In the standard development of quantum, we take that to be some identity operator. Okay, but that is not all. Okay.
Excuse me, sir. Excuse me, sir. We are not able to see the whole slide, sir. Yeah.
Pardon me?
Some part is not able to see in the slide. We are not able to see some part left. You can.
This is okay?
Yeah, now it is okay. Now it is okay.
Okay. So shall I go back, or I can continue with this point?
Yeah, you can re-emphasize the last point, sir.
Okay.
Can you please tell me the last point?
Modified inner product.
Yes, sir.
Hello.
Yes.
Okay. So
can you explain modified inner product?
Yeah, modified inner product is that say uv is Bryan-Kate notation. That means that you take u is a two-component column vector, right? U is a two-component column vector here. Two-component column vector here. Okay. Now, what you do is that when you write in terms of star notation, so basically you take u dagger. So this becomes and everything is real, epsilon 1, epsilon 2. So you don't have to take any complex conjugation. And v is the column vector. So row matrix and matrix, you do the multiplication. So that defines the norm of the inner product in the vector space. When we are defining a modified product, then what we do that u row vector, then the eta plus matrix 2 cross 2 matrix defined above multiplied by this v column vector. So again, this will get a number. So this will be defining a inner product, and eta plus plays the role of the matrix. Say just but the ds squared suman g mu dx mu. Okay, so standard in the coordinate space. So if we extend it to some other arbitrary vector space where v are vectors and eta plus is playing the role of a metric, and matrix positive definite, otherwise the length will be negative. So that's why we have ensured that eta plus is definite. Is that clear?
Yes, sir. Yes.
Okay. Now with this modified inner product, one can check orthonormality is recovered. And normalization anyway, normalization it's up to us. And I have used here in terms of u or v, I have used u tilde because when I was using the standard inner product, then I had used some kind of normalization. But as you can see on the right hand, this equation, that here I am using eta plus for the normalization. So expression for the u plus u tilde plus minus will change, and I am not calculating, but it will change. So that's why in order to differentiate the two vectors, column vectors or the row vectors, I have just put tilde. You just use this normalization, so you will get some expression. The overall constant will be different, and then check this condition. You will be seeing that orthonormality recovered. So pseudo-hermiticity, in some sense, means that it's Hermitian, but with respect to modified inner product. So this is a very important concept for the students. because up to MSc, whatever we learned, in fact, I have also learned in that way that dagger is equal to H, and where there is some underlying concept of metric that is not taught at the level of MSc, but it is assumed that the metric is identity operator. That means one along the diagonal. Okay, for the quantum mechanics case, this is oscillator. So this is 1 along the diagonal. It's infinite dimensional matrix. So that is not explicitly specified, but there are some certain where we do use a different metric in with this, which the Hamiltonian may be Hermitian, and that is that eigenvalues are real in certain region. Okay, so that means all we are calling that H is non-Hermitian. I started with the non-Hermitian, but basically, to be precise, mathematically precise, this is non-Hermitian with respect to the standard inner product, but Hermitian to a modified inner product, where the modified inner product along with the metric I have defined. Okay. Now one can check that with respect to this inner product, the matrix 2 plus 2 H is Hermitian. So that's what I say. Now, brief overview of pseudo-unitary matrices. Of course, at the very beginning, what I will do, when you some example in terms of very simple 2 plus 2 matrix. Now, I generalize it to in terms of some operator notation, and I rewrite the pseudo-Hermitian matrix O. When I call an operator, or for that matter, O as eta pseudo-Hermitian, when this relation is satisfied, that means add of that operator O is related to O through some similarity transformation. Similarity operator is eta, eta O, eta inverse. Note that eta is identity operator, so its inverse is also identity operator. Basically, you get back the standard relation that O dagger is equal to O, right? Now, I should mention here that you may find any eta for which this relation satisfies, but that does not mean that if such a relation exists, then O will have any non-Hermitian operator with respect to the standard norm will have entirely real eigenvalues. That's true. We have to find a positive definite eta. What do we mean by positive definite eta? That means all of its eigenvalues are positive. Okay, all of its eigenvalues are positive. If we can find some positive definite eta for which this relation satisfies, then there are rigorous mathematical derivations. I am going into detail. Ali Mustafa Jad's paper and review articles and all these things. Then one can show that O has entirely real space. The condition is that the similarity operator or the metric operator eta has to be positive definite. Eigenvalues of O are entirely real. Entirely real means not a single eigenvalue is complex. Okay, but there may be eta which are not positive definite, for which we don't get entirely real eigenvalues. Well, another concept is called quasi-hermiticity. Basically, we this apparently non-Hermitian operator to a Hermitian operator through again some similarity transformation, where the similarity of is rho, and rho is defined as the square root of eta plus. Note that by definition, eta plus is positive definite, all its eigenvalues are positive. So that's why square root of eta plus is also well defined. And if you find eta plus, it's very trivial to find rho, or the vice. If you can find rho, then you can find eta plus, just eta plus to rho square. Well, so this is a very important concept. That means apparently with respect to the standard norm, some Hamiltonian term matrix is non-Hermitian, but you can make some similarity to convert it to some Hermitian operator, Hermitian in the sense with respect to the standard norm. Well, I have already said. So what is the definition of pseudo-unitary matrix? Unitary matrix is, you are familiar that a matrix, if it satisfies the condition U dagger U is equal to identity matrix, this is called unitary matrix. Pseudo-unitary matrix means, again, introducing the metric operator eta. If U dagger multiplied eta multiplied by U is eta, then this is called unitary matrix. Again, as one can see that if eta is identity matrix or identity operator, then we get the standard relation u dagger u is equal to I. Okay. So if we have some Hermitian operator, then we know how to find unitary operator using that Hermitian operator. U is equal to e to the power I h. H is some Hermitian operator. If we exponentiate it with some coefficient I, imaginary number I, then U is Hermitian. Similarly, if we exponentiate any pseudo-Hermitian operator with a multiplication factor of imaginary I, then that is pseudo-unitary operator. As you can see here, that O dagger is eta O eta inverse, that is O is pseudo-Hermitian, and here U is defined as e to the power IO, and one can check easily this matrix U satisfies its defining relation U dagger U is equal to eta. Okay. Now, one point, U is non-unitary as well. So pseudo-unitary is a very special kind of non-unitary operator. So that means any pseudo-unitary operator is also in some non-unitary operator, but non-unitary operators are not necessarily pseudo-unitary. Non-unitary operator means U dagger U is equal to I. This condition is not satisfied. If this condition is not satisfied, then this is called non-unitary operator. And again, for the students, you know that unitary operator is very important even in the study of quantum mechanics. Whenever we are talking about, say, operator, hydrogen atom, Stark effect, without any dissipation term, bound state problem, then we always want unitary time evolution so that conserved, and also unitarity should be conserved. So similarly, if we consider quantum mechanical system, there are some, say, non-Hermitian term, and if the pseudo-hermiticity can be true, then one can use the pseudo and unitarity concept to see whether the time evolution is unitary or not, and all sorts of this question problem. But in this lecture, in this talk, I'm not talking about any quantum mechanical system, but just to relate things from one area to other area. Okay, so this is about all I wanted to say about pseudo-unitary matrix, pseudo-Hermitian matrices. This is a very brief review, and it will serve our purpose, this talk. But any student, if he or she is able to know more about pseudo-Hermitian matrices and pseudo-unitary operators, I can give him the references, and also through email I can explain any doubt. Okay, for the purpose of the talk, I mean, this is enough. Now I come to the second term, balance loss gain. Okay, so that is the title. Now let me start with simple harmonic oscillator x plus omega naught square x. Omega naught is the angular frequency. This is the standard you know from your BSc days. Well, and you can calculate the energy also of system. It has a Hamiltonian. You can calculate the energy, simply kinetic energy term plus, oh sorry, there is a typographical error, excuse me, it will be x square, omega naught square x square at this place. Okay, there is a typographical error. So half x dot square plus omega naught square x square. I have corrected it. Okay. Now, what happens? So d dt is equal to 0. Now, this energy, there is no explicit time dependence. The time dependence is implicit. That means solution of x is dependent. It comes through that, and you can check. You just substitute any solution in the expression of E, perform the derivative, and then check that it is equal to 0 for all time. Now we add a loss gain term. So this loss gain term, say this 1 gamma x dot omega naught square x is equal to 0. So what is the effect of the adding this loss gain term? The effect of the adding of the loss gain is that if you check this relation, that d dt is minus gamma square. It can be checked very easily. This equation you multiply by x dot from x dot each term, and then you see that you can manipulate it to write in this form: d dt is equal to minus x dot square. Now x dot square is a positive definite quantity, semi-positive definite quantity, that means 0 or positive. So rate of change of is negative if gamma is positive, is if gamma is negative. So that's why we call, when gamma is positive, we call it a lossy system. And basically, in terms of damping term, and when gamma is less than 0, then basically we get anti-damp term gaining energy. Okay. Now, what we are going to do is that this SOHO with either gain or loss. Okay. Now I am going to describe a system that is actually almost it's more than 90 years in existence. That is known as Bateman oscillator. Okay. But of course, the Bateman oscillator was not known as system with balance and gain. With this system with balance loss gain became popular after this surge in research on PT symmetric theory. Is again looking at those equations, one can see that they are basically also a system of balance and gain. But Bateman oscillator around 1931, so you can see it's more years. The motivation was that how to write down Hamiltonian for a damped oscillator. So the idea of the Bateman was there that individually the X oscillator cannot be, one cannot find the Hamiltonian. Similarly for Y, but what Bateman did is that he did a time reverse version of the X oscillator. Time reverse version means you see that if t goes to minus t, then you get the second term gets changed, because x double dot there is d2 dt square and another variable. So you get a second oscillator, and the system as a whole, is a conserved system. Either the X oscillator is not conserved because the damping, or the Y oscillator is not a conserved system because there is a supply of energy. But if you have the X oscillator, Y oscillator as a total system, then write down a Hamiltonian and there is something conserved. I would like to side comment. Of course, this from this Center for now it's Department for Nonlinear Dynamics. There are research where one can construct the Hamiltonian even for the oscillator or the Y oscillator. Okay, so that is possible. But here our motivation is only on balance loss gain, not on Bateman oscillator. We'll see that if there is a coupling, then there are miraculous things happens and interesting theoretical predictions and in some cases observations of physical phenomena. Okay, here our motivation is not to confine ourselves only for the Bateman oscillator. Now I have to what do we mean by balanced loss gain? If you note carefully, then you can see that the coefficient of the loss term is gamma, coefficient of the gain term is minus. So if you sum them up, gamma plus minus gamma is equal to 0. So this is very elementary definition, that coefficient of the loss term and gain term equal to 0. So that's a balance. Gain and loss are balanced. But in reality, we have, say, in the first equation, we can write some term proportional to y also. Second equation, we can write some term x dot also. So there are some definitions, the direct dissipation, indirect dissipation, all this. So we have to give some definition. What do we mean by a balanced loss gain system? So that's what I do now. So for compact presentation of results, I just redefine X as xi1 and y as xi2, x dot as xi3, and y dot as xi4. So you know how to write down second order equation of motion in terms of first order equations of motion. So I do in my next step. I introduce some fields F1, F2, F3, F4 as this, and one can check that this equation with the definition of xi1, xi2, xi3, xi4, and f1, f3, f4 can be written in this form. Okay, xi dot is equal to function of xi1, xi2, xi3, 4, which are specified in this equation. Now, I will be using some results because there is derivation in standard nonlinear dynamics. That's tricky and lengthy, so I just borrow the result that volume in the position velocity state space, if there is a then you see the phase space is conserved. So that means divergence in xi space. So that means del xi1, del xi2, del xi3, del xi4, and f is vector f1, f2, f3, f4. So the xi state space is conserved is evaluated by this in our notation. Divergence xi dot f is equal to 0, and one can check easily that this is indeed satisfied by this equation. But if we would have taken here, say, gamma 1 and gamma 2, where gamma 1 and gamma 2 are not identical, then we could not have got this equation satisfied. Divergence f is equal to 0. Okay, so this will be our definition. We could take any many component system, say n variable system, and there our definition of a system with balance loss gain, that we write it in terms of first order equations and use this equation, that divergence I dot f is equal to 0. If it is 0, then we define it's a balance loss gain system. And in fact, for such systems, for large class, not all, one can write down the n also, but today's talk I will not be going into that. Okay. Again, for this particular example, one can define this quantity E dot y dot plus omega naught square xy, and one can see that concept. Again, just like the previous case, dE dt is equal to 0. Good. And the system is Hamiltonian. I'm not writing down the Hamiltonian here, but one can write it down quickly. Now, this bedpan oscillator, what happens that this oscillator and this oscillator, they are decoupled oscillators. No coupling between the two. So one is losing energy, one is gaining energy. What happens if I couple them? If we couple them, that will introduce some interaction, and it may happen that gain and loss, for some values of the parameters, there is an equilibrium position, so that loss of energy by the first oscillator, the X oscillator, is supplemented exactly by the due to this coupling by the second oscillator, which is gaining energy. So there is sharing between the two. Then we may get some equilibrium state, and that's an interesting point. So I am just presenting some model, coupled oscillator with balance loss gain. You can see that this one we had already considered, this part we had already considered. Okay, so what is new? The new term is this. This new term is this coupling term, linear coupling, and there is a nonlinear coupling. Okay, basically this is linear coupling, and this nonlinear coupling, as I mentioned later, is basically, there is a very famous model. It's the rational Calogero model. So it's a part of that. Now, one can calculate the relations involving these parameters, whether there is an equilibrium or not. So these are the equilibrium state in the red color. If gamma, omega naught, and epsilon 1, epsilon 2 satisfies these relations in the parameter space, then we get equilibrium state. That is periodic solution. There is no decaying, no gaining of energy. Decaying means that some solution goes to 0, and gaining means it diverges to infinity. But within this case of the parameters, this particular model, you get periodic solution. Now, for epsilon is equal to epsilon 2 is equal to minus omega naught square, as I said earlier, that 1 by cube type potential, they're very special case of potential in particle known as rational Calogero model, but here only it's for two particle. So if we epsilon 1 and epsilon 2 is equal to minus omega naught square, then this model is a rational Calogero model. If we take epsilon 1 and epsilon equal to 0, then this is called a this Calogero model, some other variant, Sutherland variant. So there is no external confining potential. And if we take this one, epsilon 1, epsilon 2, as well as this 1 by cube term is equal to 0, this is called Bender, coupled simple harmonic oscillator Bender. This appeared in physical review A. After that, this balanced loss gain system got a big impetus after this paper. And not only that, the model for epsilon is equal to epsilon 2 and G is equal to 0, it describes some oscillation. This mathematical model for some oscillations observed in microcavities. The experiment was observed before the theory, and in order to explain those experimental results, this was proposed as a mathematical model. And after that, there are many on this balanced loss gain system, their Hamiltonian formulation, and their quantization, and all these things. Well, and one more thing, I will not give any example, but I just name fractional Calogero model and coupled oscillator model. One can find this model, find with this limit discussed here, one can find exact solutions. Okay, there is no pseudo-unitary transformation or anything like that. One can find it. Now, for one can define similar n-particle Hamiltonian, balanced loss gain system, constant Hamiltonian, exactly solvable models, but they are also, one uses some kind of transformation. They are not really pseudo-unitary transformation, but some other kind of transformation. There is some underlying relation between those transformations and the pseudo-unitary transformation. Yet we have not been able to find it out, or any other group, those who are working on it, have not been able to find out. So don't use an example of exact models for n-particle system with balanced loss and gain. Okay, but I present here this mechanical model just to give you the idea for the mechanical system. How do we introduce balanced loss gain system? That was the part. Okay, so are there any questions?
Sir, I have one question. Is it possible to find three-particle case, sir, with the coupled loss and gain?
Find exact solution?
No, equations, models.
Yeah. Many, even n particle, where n is arbitrary number of particle.
So, do you have any explicit example for three-particle case? Balanced loss and gain.
Yeah, I have explicit example. Yeah. So, for example, I can write down the famous Toda equation. Okay. Okay. Just let me ask you one thing. That is your question with the emphasis that can one go beyond 2, or how do we write down balanced loss gain system using 3 particle? Which is the emphasis of your question?
Yeah.
Hello.
Yes, sir. Can you go to the previous slide, sir? The equations. No, equation. Yeah. My question is, precise question is it possible to have 3 equations with balanced loss and gain?
Yeah, 3 particle system. What they do?
Yeah.
Suppose I introduced here z dot plus omega naught square z. Say I give some coupling here, either x. Sorry, I mean it's a tough. Yeah. So I give some coupling, say epsilon x, okay, epsilon 4y plus some other. Okay.
Yeah.
So this is a trivial generalization from 2 particle to 3 particle. This balance loss and gain is pairwise. Okay, but I can write this way also. Say x dot gamma 1 x dot y dot gamma 2 y dot z dot plus gamma 3 dot plus appropriate interaction and coupling term. Okay, that is also possible. I have to write it then that gamma 1 plus gamma 2 plus gamma should be equal to 0.
Okay.
Okay.
Okay. Yeah. Okay. But I am not seeing many papers on this direction. Are they interesting or not, sir?
No. Okay. So I'll inform you. In fact, this N particle system, my ex-student, Devdeep Shina, and we have thorough work on any N particle system, how to construct Hamiltonian system, define balanced Gaussian system. Okay, I have also one paper, a single paper where I have clarified all these points. This how mathematically define what's the balanced Gaussian system. So I'll give you after the talk. Okay.
Okay. Okay. Okay. Thank you.
Okay. Now we talk about this non-deterministic classical field theory. This is very familiar. In fact, from Department of Nonlinear Sciences at BDU, there are many works on nonlinear Schrodinger equation, and for a few decades. But for the completeness, just let me introduce that the students, if this term where it's written nonlinear, if that term is not there, but if that term is replaced by some Vx function of x phi, then you recognize this as the Schrodinger equation, standard quantum. Vx would be, say, for example, I t. My handwriting is too bad, so delta Vx. So if this blue color, whatever handwritten equation is there, that is the standard linear Schrodinger equation, and Vx is the potential. Linear Schrodinger equation is what is there inside the box. Okay, and there are different kinds of nonlinear. I'm here choosing the famous one, the cubic nonlinearity. Okay, here since we'll be talking about classical field theory, or the classic psi xt is a complex scalar field, and with the standard notation that psi means del psi del t, psi xx, del 2 psi del x square. And this equation appears in the optics. Okay, very important to many optical phenomena. The classical optics studying from 70s, and even nowadays also photonics, photonic lattice, and all these things are coming up, new ideas, and everywhere this relevant. This is very relevant, means it's modified form, but the thing is that this is nonlinear Schrodinger equation. If we add some confining potential, that means if we add some term like this with this equation, then that is Gauss-Pitavsky equation, and for the Bose-Einstein condenser is very useful. And then plasma physics, gravity waves, alpha helix protein dynamics, the list is very, the famous ones have included here. It has a relevance. Well, now mathematical structure is also very important. One, the Hamiltonian for this. Okay, this is the expression for the Hamiltonian, and classical system is integrable and solvable, and it admits solitary solutions. Being in Department of Nonlinear Science, and there are many works on solitary solutions of various types of nonlinear equations. So I hope you are familiar with that. I'm not going to explain that. And integral. So you may have heard. Basically, if you are taking a course on advanced classical mechanics, then you find that some quantities which are Poisson bracket, if it is time independent, in the Poisson bracket of those quantities of is equal to 0, then we call this linear integrability. Okay, different thing. But within the field theory, finding an integrable system is very hard. Okay, so that way this classical system of nonlinear Schrodinger equation, example of integrable system, and furthermore using some other very famous technique, scattering transformation, it's solvable. So it has immense impact in the development of nonlinear science, this nonlinear Schrodinger equation. Well, not only classical system, quantum system, this this interaction nonlinear part, basically, when you will learn, students will learn second quantization, or if some of you taking particle physics, field theory course or particle physics, you know what is second quantization is. This, if second quantization I star SAR, basically it represents some delta function kind of thing. And it physically describes delta function hardcore Bose gas. Okay. Then the quantum model is exactly solvable and integrable. These, I mean, there are these are famous names. Just cite the name so that you can relate in future that you have heard this name somewhere. Liebnier model and also Tonks-Girardeau gas is very important in the context of the Bose-Einstein condensation, and one can calculate the correlation function for this model. So this is a very achievement. There are very few models we find exactly solvable. We may find integrable, but finding exact solution is not easy. And then we are calculating the quantum correlation function. There is a very okay. So you understand how important this nonlinear Schrödinger equation is from the viewpoint of classical mechanics as well as quantum system. Now, how do I take this nonlinear Schrödinger equation with some gain and loss term? Well, so for this case, I add this term, okay, I gamma psi, where gamma is some real parameter. You can define, say, density rho as psi star psi, just like Schrödinger equation also define probability density and probability current. With the same spirit, you can write rho is equal to psi, and that you see that with normalization factor, this h bar I, m, h bar m, velocity of light, all these things are not there because I am working in class and non-linear history, but you can relate with this expression, okay? And the way you derive the continuity equation for the linear Schrödinger equation, you follow the same method, and you can arrive at this continuity equation. So density del rho del t plus jx, so this is my jx is minus 2 gamma. You see, gamma is the term which is responsible loss and gain, right? So if gamma is equal to 0, then the standard continuity equation we get del rho del t plus x is equal to 0, and we can define the concept church. But if gamma is non-zero, then things are not concept. There are source and sink terms. Well, now we define for well-behaved psi. Well-behaved means that it vanishes, and we define a quantity n as dx rho psi star psi. Then you integrate this equation with respect to x and show that this is the equation, and you know how to solve this. You see that n, basically n in field theory defines as a number operator. In the context of operator, it is called power. You can solve it, and you see that n naught is some constant into minus 2 gamma t. So if gamma is positive, n decreases. If gamma is negative, n increases. So this is the manifestation of gain in the context of nonlinear Schrödinger equation. Now, how do you consider balance loss gain with nonlinear Schrödinger equation? Again, just as in the case of mechanical system, what we do, we take a copy. That means have to, if one field is receiving energy, then there should be some term, some field which is losing energy. Okay, so that was the idea of Bateman model or the subsequent. And you can see that this is the gain term. Okay, this is the loss term. I have also introduced linear coupling. There are two fields, psi 1, psi 2, and this psi 1 is coupling to psi 2, psi 2 is coupling to psi 1. This equation, this is the standard dispersion term. And in addition to linear coupling, I have nonlinear coupling also, where M1 and M2 are 2 cross 2 Hermitian matrices, delta, beta are real parameters. And depending on the physical situation, one take particular forms of M1 and M2. At this level, the equation will be defined in this way, where M1 and M2 are arbitrary. Now, for our purpose, this equation can be written in a very compact form. So, in order to write compact form, what we do, M1 is equal to M2, that means M1 and M2 are identical, and introduce Pauli matrices, sigma 1, sigma 2, sigma 3 with standard representation. And for the Pauli matrices plus minus, these are raising and lowering operators. One side comment, if we don't assume this one, the M1, M2 is equal to M, we can write it in a compact. But to make things very simpler, I have M1 is equal to M2 is equal to M, but it is possible. How it is possible? Because that any 2 cross 2 matrix can be expanded in terms of 2 cross 2 identity matrix and 3 Pauli matrices. So we can expand M1 in that way, and psi 1 and psi 2 we can use this sigma plus minus as an operator and we write it. So, but anyway, I'm just giving the information, but not going into detail. For our purpose, we take M1 is equal to M. Now, if we do that, equation can be written in this form. Okay, linear coupling can be expressed as this, and loss gain term can be written as this. All other terms remain this. Now, with this, we generalize it to n component. We have n fields: psi 1, psi 2, psi 3, psi n. Okay. In order to do this, we introduce n cross n matrices B, T, and we define A in terms of B and C as this. B is Hermitian, C is Hermitian, but A is not Hermitian because B is equal to A is equal to B plus IC and M. Okay, M is also Hermitian. Now the condition for balance again is that this gain or loss is coming through C, so the trace should be equal to 0. If the trace of C is equal to 0, then this is a loss gain system. Okay, and how to express these matrices? For the 2 component case, we use these Pauli matrices, which are the generators of SU2. For any n component, what you can do, we can express this in terms of generators of SUN. Those who are not familiar with SU2 and SUN, this is basically SUN is the unitary matrix of n cross n. So you know unitary matrix. What is so special about it? When you take unitary matrix with determinant is to 1, then we call it special unitary matrix. In fact, any unitary matrix, one can show the determinant is plus 1 or minus 1. So we are restricting to the plus 1. That's why this is special unitary sector. And the generators are well known. I mean, Google search or any standard book on group theory or particle physics, MSc or any book will give you the expression for at least SU2 and SU3. With this notation, for any component, this is the expression. Okay, this is the this vector nonlinear Schrodinger equation. Note that this A is B plus C. Okay, so this is the term is contained here. Okay, and this is the standard dispersion term. This is the nonlinear. Here I have written is D naught. Those who are familiar with the field theory, course, not basic field theory course, say non-abelian gauge field or something like up to that, then you know that this has the form of temporal component of the covariant derivative. This is just for the information. Go into the detail about it. So D naught resembles temporal component of covariant derivative with complex potential, but it has significance. So that's why I mentioned this connection. This is not simply meaning that this looks like that. Okay, one can exploit this relation to do many calculations. Okay, now since we are talking about nonlinear Schrodinger equation, this term Heidegger M psi, one can take specific forms of M such that physical model in optics can be reproduced. Say with suitable choice of M or the previous model where we had M1 and M2, can introduce self-phase modulation and Fourier mixing terms. These are terms from the optics. I mean, particular form of interaction arising in the context of optics. But what I want to say, this is not simply mathematical formalism, mathematical development. One can talk about physics also within this formalism. So with specific choice of M, suppose if I introduce self-phase modulation, cross-phase modulation, and Fourier mixing term, then basically the standard vector nonlinear Schrodinger equation, what makes it different is term where there is linear coupling among the components and there are damping and anti-damping terms. Right? Now, for n is equal to 2, this model has been studied extensively, mostly numerical in the literature. Very interesting features. Some of them are even experimentally realized. Say it admits solitary solutions in spite of having a loss term and gain term. It admits breathers. It has power oscillations, that is power oscillates in times. Power oscillation is a manifestation of specific form of this damping and anti-term. It has exceptional points. Exceptional points, there are in the general parameter space, there are eigenvectors with different eigenvalues, but if we vary the parameters, then there are certain points in the parameter space where the vectors as well as the eigenvalues coalesces, and it gives interesting mathematical phenomena even in the context of quantum mechanics or other places. This is just in some sense opposite to degeneracy. Degeneration means you have the same energy eigenvalue but linearly independent eigenvectors. But here, if you vary the parameters, they are distinct states with different energy and different vectors. But at some point, or maybe there are several points where everything coalesces to a single point. These are singular points, but it has some interesting physical applications. Okay, and then nowadays people are talking about solitonic communications. So these loss gain terms also can be used successfully for solitonic switch. So there are many physical applications, and I want to give you the feeling this is not only mathematical, pure mathematical development, but with model, if one wants, one can find his or her of physical model. Okay, now this is more important. The continuity equation. So the continuity equation for the linear Schrodinger equation, one derives continuity equation. One can calculate the continuity for this, and this is the expression. Okay, now note this. So depending on whether this is positive or negative, there is a source or sink term. Okay, and this is a standard definition of density operator. But what is important is that if we define, say, Q tilde in terms of rho tilde, this is not conserved because of the source and sink term. What is important is that we can define a modified density operator, and if the A is M pseudo-Hermitian, I have already defined what is M pseudo-Hermitian, A, then with this definition of rho and this definition of current, one gets this del rho del t plus del j del x is equal to 0. Continuity equation is recovered. Okay? So again, the importance of this Hermitian matrices is apparent from this derivation. This rho tilde and j tilde is not giving equation, but for a non-standard rho and j, and give the quantity conservative continuity equation. So this is good. We can define a charge dx rho that is constant. Okay. Now I am running behind time, so what I should do is that I will keep this Hamiltonian formalism. I just mentioned the whole thing. One can get a one can write down a Hamiltonian. Of course, this is not a real valued Hamiltonian. This is a complex valued Hamiltonian, and if one quantizes, then there will be very intricate problems. Okay, so I just keep this since I'm running out of time. Okay, now example I would like to mention is that nonlinear Dirac equation. Equation you are familiar with in Lorentz covariant notation. Gamma mu del mu minus m psi is equal to 0. This is the Dirac equation. Forget about this term. Forget about this term. Now here, what I have done, I have introduced this term m to gamma phi. Okay, some extra term. M2 is equal to 0 and f is equal to 0, you get standard Dirac equation. But if M2 not is equal to 0, we get a non-standard Dirac equation. And if f not is equal to 0, we get some nonlinear interaction, the nonlinear Dirac equation. And psi here should be understood as Dirac field or Dirac minor. Okay, Dirac field is better because we are not doing any quantum mechanics. So now this for M2 is equal to 0 have been studied in the context of particle fields, and they are very important in the development of particle physics. And some of the models are studied from 90s onwards in the context of strongly correlated systemic conditions. If M2 is equal to 0 and F is taken with from that this is a function of psi bar psi only, then this is called solar model. If this model is considering one space one time dimensions, this is called Ross-Neveu model, whose model is very famous in the context of particle physics. And again, if M2 is equal to 0 and F is take current interaction, those who are familiar with Dirac equation can identify J vector current, psi bar gamma, 4 vector current, psi bar gamma mu psi. So this J mu, this is called massive string model, and this massive string model in the context of strongly correlated system, it is again popular in the context of lower dimensional system, basically system. So again, you see that for M2 is equal to 0, but F is equal to 0, whatever we are talking about, we have a very viable physical model. Okay, but by introducing M2, we are introducing loss and gain. So last term non-Hermitian for M2 not is equal to 0, that we have introduced. How to cast it in terms of balance loss gain? Okay, this part not very easy to visualize, but you see that when I write down the equation, this gamma mu is gamma matrices, and you know that gamma mu has various types of representation. In one particular representation, one can see or identify this mass term M1 plus M2 gamma 5 as the loss gain term, only that balance loss gain term. How? So I am taking this particular representation. Okay, so if you substitute it here, then the equation, this one, you can write in this particular form. And you can see that IM, where A this is like A matrix in the context of nonlinear Schrodinger equation. Okay, of course, the dispersion term is modified because this is that equation, and nonlinear term is also different depending on what F you choose. M1 sigma 1, I M2 sigma 3, outer product I2. M1 sigma 1, I M2 sigma 3 is I M2, M1, 1 minus IM. So you can see balance in terms IM2 minus IM2. If you do the outer product, then basically you get a copy of the 4 cross 4 matrix, a copy of this. So balance loss gain system is manifested. But when you are working to find solutions or something like that, you can use any representation which is convenient to find the solution. This is just to see that again this cast into the formalism I'm talking about balance loss gain within that discussion. Again, if one defines the standard definition of charge psi dagger psi, this is not a conserved quantity. You the Dirac equation, continuity equation, that same technique here, and that this is not a conserved quantity. Okay, but as in the nonlinear Schrodinger equation, if we define some psi dagger psi is modified probability density, then we can have a conserved charge, provided these relations are satisfied. These are very complicated relations. Okay. Now, first consider standard linear Dirac equation. Take F is equal to 0 because that's a nonlinearity. So this condition goes. This condition is equal. Okay. Then we try to solve it. And just the form with inspection, one can show that for F is equal to 0 and mod M1 and mod of M2 satisfying this relation, one can find it as this I4 plus M2 by M1 gamma phi. Okay. This condition is not there, then this is not positive difference. Okay, so this condition is introduced to make it positive difference. Okay. But what happened about the nonlinear Dirac equation? Nonlinear Dirac equation, we have to take F equal to 0. Are there any solutions for eta plus? Yes. If okay, so before that, one more comment I forgot to mention, that I am talking about M1 greater than M2. What happens? This M2 is equal to M1 plus M1 or minus 1. There is interesting physical phenomenon. Okay, this probability current shows chirality whenever this M2 is equal to plus minus M1. What do I mean identity. For positive M2 is equal to M1, it receives non-zero contribution only for the right-handed component. M2 is equal to -1, it receives contribution only for the left-handed contribution. So it has some physical effect, whether it will be observed or not, that is not known. I mean, for that we have to, for mimicking some physical system. Okay, the next, that when F naught is equal to 0, there are various solutions. I just mentioned one. Psi bar in psi, F is of this form. Then W is Hermitian, because this is the condition that W has to be Hermitian, but W is this. Then Hermitian for eta plus or M if we take this one. Okay. Okay. So I have explained what I wanted to talk about, that appearance of balanced Lagrange system. I started with the mechanical system, then nonlinear Schrodinger equation, that's basically non-relativistic field theory, and then nonlinear Dirac equation. Now coming to the main topic. I took too much of time for introduction, but anyway, main part is very difficult. That how do we use some pseudo-unitary transformation to map it to exactly solve it? Okay, that's my topic, central theme. Okay, and I will for only nonlinear Schrodinger equation, but one can trivially extend the method to show that specified nonlinear the Dirac equation is specified nonlinear interaction. The method goes not only nonlinear Schrodinger equation. If we remove the dispersion term, then that basically describes what is known as oligomer, okay, or the discrete nonlinear Schrodinger equation, okay, and that part is also can be. I mean, that part is also can be put framework and can be solved analytical, exact analytical solutions. One can find exact solution. Okay. So with this, now I have roughly 30 minutes. What I will do is that I will show that how the M pseudo-Hermitian A nonlinear Schrodinger equation, vector nonlinear Schrodinger equation, can be mapped to the same equation without linear coupling and what is that called? Lagrange term. So I define psi as u phi, where phi is a scalar field, and my u is minus IAT. Remember, A is there, B plus C. B is linear coupling, and the C is Lagrange term. Okay. Now, after this substitution in the original equation, we get this equation. Okay. That note that there is no linear coupling on Lagrange term, but phi dagger M phi is modified as phi dagger U A mu phi. Okay. Now, what is the definition of pseudo matrix? That U dagger mu is M. If pseudo matrix U dagger mu is equal to M, then we have phi dagger M phi. That was the original interaction. So I am mapping. Say this is the pseudo transformation. U dagger mu is equal to M, or A dagger M A M inverse. So through this transformation, I am mapping my original equation in terms of equation. Well, this is exactly solvable for specified form of M. In fact, not specified form. One can make canonical term into specified form if for any M. Okay, this is in general known as Markov system. Okay, so this is exactly solvable. So original problem, if A is pseudo-Hermitian, can be solved exactly. Known solutions of this equation 1, can be used to get solution of the original solution. Now, one might say that, okay, this is a transformation, so what's so big deal about it? That this is non-unitary transformation, or to be specific, pseudo-unitary transformation. So that means psi dagger psi and phi dagger phi not identical. Psi dagger psi is equal to some factor, some space-time dependent factor times phi dagger phi. For this particular example, this will be time dependent, and that's the source of power oscillation, because psi dagger psi is defined as power. Psi dagger psi is some function of t multiplied by phi. Okay, phi dagger phi is the exact solution of Markov system depending on M we choose. Okay, so this is the beauty. Had it been a unitary transformation, then okay, this is just similar transformation, just a simple transformation to solve the problem. But the physical setup of these two systems described by phi and are completely different. So that is the main thing. Now, this transformation goes through. That means linear coupling and loss gain transformation, even if A is not pseudo-Hermitian. Okay. So what happens to that? Well, in that case, what happens? This M matrix, it becomes. Suppose we start with time-dependent M, then through this transformation we can independent, exactly solvable model. Okay. If dependent M, then due to this transformation, time-dependent NLC gets modified. But this part one has to solve exactly. It's not direct mapping to Markov system. Okay. So I mean these are just mathematical details. I am running of time, so I am not describing these mathematical details. Okay. And then finally, this for the two-component case. Back to the two-component case after doing all this general method, and then here we construct positive definite with this condition, and then M pseudo-Hermitian for the given M and A. This is the condition M pseudo-Hermitian A, where we have defined alpha as beta as complex parameter with mod of polar decomposition for alpha and beta, and this is the condition. If this condition is satisfied, then we pseudo-Hermitian A. If we get M pseudo-Hermitian A, that means psi is mapped to the Markov system exactly without any extra time dependence. Well, and so in order to calculate power oscillation or exact solution of U, in terms of psi is multiplied by e to the power minus IU, we have to find expression of U. Those who are familiar with the Baker-Campbell-Hausdorff formula, they can use to expression of U from this. Okay, this is easy. Okay, and also for this U, note that theta has expression mod of beta square minus gamma square. So if theta is imaginary, then this cos theta periodic function becomes hyperbolic. Okay, and if U is and this U multiplied with phi, that gives psi. So if it is hyperbolic, that means you don't have bounded solution. But we want bounded solution, because if phi is Soliton solution, then U makes it unbounded. We don't want that. If you want, then fine. Then any beta and gamma hyperbolic function is also acceptable. But we don't want that. So the consistent condition that it should be periodic function, not hyperbolic function, is that gamma should be within this range. Okay. So for the two-component case, gamma within this range, we can get exact solution for the psi in terms of which are in presence of linear coupling and balance loss and gain. Okay. Best. Okay. So there are some other consistent condition also. This is equivalent basically. This one is solved if gamma is greater than 0 and if gamma is less than 0. Okay, and this is the expression for power. Okay. This is the power oscillation. N is the power oscillation. Okay, here. And if balance loss gain is not there, then one can show. I have not given the detailed expression. Basically, N1 and N2 depends on gamma. So if balance loss gain is there, gamma is equal to 0. So N1, N2 is equal to 0. So there is no power oscillation. Okay. Let's take hyperbolic solution of nonlinear Schrodinger equation. So this is okay. This is whatever I said just now. Okay. Okay, so the generalization part I will skip because I will take some questions. So already it's 4:55. So I am skipping the generalization part. There are various generalizations recently about PT symmetric potential or non-local nonlinear Schrodinger equation. Say This is the non-local nonlinear Schrodinger equation. This is addition to the system of exactly solvable models. Okay, so these are generalizations of nonlinear Schrodinger equation, and one can incorporate all three in terms of in terms of balanced Gaussian system. One can input balanced Gaussian system for these two cases, and in fact we have done that. Uh, my current my student Supriya Ghosh, and we have done, and that is the this is the archive number. Okay, and here whatever it, I mean, this is more general in the, we have included some external potential. We have considered loss gain coefficient independent. We have considered nonlinear interactions to be space-time dependent. Yet we find exact solutions, of course, under specific set of nonlinear modulation, specific time dependence, and specific complex potential. The model, one might get the impression that psi dagger m psi, so very it's applicable to only Manakov system. That is not true. It can be applied to other systems. So the detail is given here. Okay. So I skip, and then finally this is summary. Whatever I have done, I have introduced balanced loss gain system in the context of mechanical system, in the context of nonlinear equation, in the context of nonlinear Dirac equation, and used some method PseudoUnitary transform to map them to known exactly solvable model, and that has been exemplified by a two-component vector nonlinear Schrodinger equation with balance gain. Now there are various directions also. Say for n greater than 2, that means beyond 2, we have not done anything. There are some primary results, but we have not published it anything. But that's true. Okay, and then this nonlinearity, this archive with Supriya, that is some results, but for the most general case, there is no result yet. And the final thing, what is more important to me, or what I personally like to explore by my group or somebody else, is the quantization of this system and what is the effect of this kind of complex valued system. Okay, so that I would like to pursue. And of course, these oligomers and all these things, these are also some cases exact solutions have been found, but some physical model of oligomers can be solved exactly, and some properties which can be verified that can be predicted will be very good. So the references to this is that this first one is on unitary transformation. This second one, this is the conference proceedings, but the review all of our earlier works are there, and it's there are many elementary things I've discussed. I tried to discuss in a very way. So this is a conference proceedings and available from the archive. The recent work with Supriya is there in this archive. Okay, thank you very much. Thank you again for inviting me and organizing this conference. Thank you, students, teachers, whoever are there. Any other questions and people have patience, I'd like to answer to those. Thank you again.
Thank you, sir. So it's time for questions, clarifications, and suggestions. Prashant, you can raise your question now.
Yeah, Prashant Panigrahi.
Prashant? Prashant? No. Okay, what about others? Kanna, you can raise your question.
Thank you, sir, for thank you, Professor Ghosh, for a nice, interesting talk. If we introduce higher order terms in the NLS system, coupled NLS system, can we generalize can one generalize this method? Will it be working for that also?
Higher order terms, loss gain terms, higher order loss gain terms, or
Higher order linear terms, derivative terms, like Sassa's equation and all.
yeah, if the dispersion term,
Yeah.
yeah, it will go through trivially. There is no problem. But if we introduce, for example, nonlinear dissipation gain loss term, then I do. But there may be some specific forms for which it is applicable. Okay. But if you take higher order terms, that means the dispersion term, they go trivially. Again, if you nonlinear coupling term, say if you go beyond cubic, say fifth order or sixth order or whatever maybe the physical demands, there should be some particular cases for which it is applicable. But nonlinear gain and loss, if that is a which is I psi cube type of term, that I don't know to see whether it works at all or not, and even if it works, what are the limitations?
Okay. One more question
Am
is
I able to answer your
regarding.
question?
Yeah, I got your point. One more question is regarding the coupled model that you have discussed with Professor Senthilvelan. There you have a rational term g of x, some rational term with the coefficient g. If it is not rational, just x cube and y cube, is it integrable or is it solvable? That coupled model.
Can you repeat your again? I cannot
Yeah.
hear properly.
With the Professor Senthilvelan, you discussed a model, a coupled oscillator model. There you have a rational term. There, if we instead of rational term, if we have a term like x cube and y cube, is it still solvable there?
So let me. I mean, if I understand, then let me see that model. Is the model here
Yeah.
you're talking about?
This is the one. Yes.
Yeah.
Yes. Instead of having the last term rational term, if we have just x cube and x cube y squared, x squared y in the top equation, like the Manakov equation, x cube plus x squared y. In the below equation, x squared y and y cube. It's like
so you are asking a specific form of nonlinearity. Okay.
yeah.
But what I am to say is that we have some where if these two terms are replaced by say x cube, okay, say and similar this term, some cubic term is replaced, then we do get exact solution, okay. But in fact, this Lakshmanan and one of his collaborators has a physics report. These cubic equation solutions are nicely summarized. We have seen that within the context of balanced loss gain system, this cubic interaction here, all of those go through easily. And in fact, we have borrowed those solutions to construct solutions for balanced loss gain system. There, what happens, you see that if potential is translationally invariant, then there is a very fiction. For example, if we take epsilon 1 is equal to 2 is equal to minus omega 0 square, okay, then as you can see, that this is of the form of x plus y. Okay, because epsilon 2 is minus omega naught squared, so we x minus y here, we get x minus y here. Okay, here
Okay.
this is also x minus y. If we add these two, then this nonlinear term adds up to 0. Okay, so that means that this x plus y, if we define for this problem, this one, x plus y as z1 and z2 as x minus 1, then z1 is a linear equation, right? Then
Yes,
z1 is
yes,
a
yes.
equation which can be solved analytically. Only problem is whether z2 part, for which this term will not cancel. Addition of these two terms will not be equal. That gives a nonlinear equation. Okay, so for this kind of thing you are mentioning, if we substitute these at some x for y cube, if it has translational and invariance, that means it's a function of nonlinear term is function of x or x minus 1. Then again the same trick can be used to decouple terms of z1 with this x plus y and z2 x minus y. So solve for z1 and substitute back in the z2 equation. Most of the cases, what happens, we get back whatever I referred to that for Professor Lakshman and his collaborator. All those can be accommodated within this formula. And the solutions are very interesting. Not necessarily that always we get solid, we get distributive solution in terms of Jacobi elliptic function, all these things. Okay, very interesting. But the condition is that we have to have nonlinear interaction for this particular case. It should be x minus function of x minus y. For n particular case, there are other conditions. We define some kind of rotational symmetry. Okay, this is not standard rotational symmetry. That means R is defined as x square plus y square, but R is defined square root of x square plus y, but R dimension. Then also, I mean, again, one can talk about many solvable models. What is more interesting is that we have a kind of generalized Calogero-Shadal model. This is not considered the standard Calogero-Shadal model, for which, for the quantum mechanical case, for n particle case, are able to find exact correlation function. But the difference is that standard Calogero model only say 2.3.4 functions can be calculated. Here only even point correlation function can be calculated, 2, 4, 6. Okay. So am I able to answer your questions, Professor?
Yeah, yeah, I understand that. Thank you.
Sir, please go ahead.
Thank you very much, Professor Bose, for a very interesting talk. So I have a question. You are relating the coupled nonlinear vector nonlinear Schrodinger equations or coupled nonlinear Schrodinger equations without valence loss gain terms through appropriate transformations. Can you identify these transformations through symmetry analysis? Can you identify
No,
the
I have
kind
not
of...
done any
Pardon?
Professor, are you talking about Tenedeve analysis and all these type of things?
No, symmetry transformations are like Lie symmetry analysis. So through Lie symmetry analysis, can you identify the kind of transformations that relate the coupled nonlinear Schrodinger equations without loss gain terms and with loss gain terms? Because in some of the other equations,
those kind of analysis. Yeah, please continue.
No.
Please continue, Professor.
I mean, you made some. You said such transformations have been identified or not?
Can you repeat it again?
No, I'm asking whether you can identify suitable symmetry transformations connecting the couple nonlinear Schrodinger equations without loss gain terms and with loss gain terms.
We have not undertaken any project along this direction, but it should be possible. This is my expectation, but we have not undertaken any investigation along this direction. Why my expectation is that, say, if you are talking about Lie symmetry, so here we can see there are conserved charges. Okay, so if we take, and also we can have Lagrangian Hamiltonian formulation. So if we take this Noether's theorem, then I should expect there should be some corresponding symmetry transformation corresponding to this conserved quantity. Okay, from that idea, I am expecting that there should be some symmetry transformation related to these two systems, namely one where there is no and one where there is loss gain. Okay, but we have not undertaken any project in this regard. That's a good suggestion.
Okay, thank you very much. It was an enjoyable topic.
So, any other question? Sir, it's already late, so it's not getting any questions. Maybe the students may write to you. Prashant, you have a question. Sir, can you read chat box? Shall I read?
Yeah, I can read it.
Yeah. Please.
So can you repeat it again? It flashed in on my screen and then again it went. Prashant, can you repeat?
Can you retype it again, Prashant?
This is incomplete. Prashant, I can see that this coupled laser cavity, and then after that dot. So what is your question? Sir Shantil Velan, you can read it for me.
Yeah, sir. Coupled loss gain nonlinear Schrodinger equation can be used for laser cavity dissipative systems. Is there any observation of self-similar solution for this equation system? So his basic question is it possible to derive self-similar solution?
Self-similar solution.
I think again, as Professor said, we have to try with Lie symmetry analysis, sir. I think we can derive self-similar. Self-similar solutions.
I make one comment.
Yeah.
Yeah, what I can say is that, often I cannot remember, but about all the Soliton solutions in this balanced laws nonlinear Schrodinger equation, there is a review article by Konotop. It's mentioned in my presentation also somewhere. So there, whatever results are there up to 2018 are nicely summarized. So you can look to that. Often, I cannot say whether it's there. Already found it or not.
Better. Yeah. Prashant, you may have to. You have to try with some other methods. Is there any other question? It's getting late. Okay. Sir, okay, he accepted that. Yeah.
Yes.
I think I'm not getting any questions from student side, sir. So if not, let us conclude the session. So I want to conclude the session by thanking Professor Piju Bose for accepting our invitation and giving a very interesting talk in this forum. Thank you, sir. Thank you for delivering a talk in this forum, sir.
Okay, thank you very much.
I will write to you other details by email, sir. So if you want, you can leave. Yeah. Thank you.